Everyone, thank you so much for being here and sparing a few hours from your busy lives to come and support me and watch my PhD defense. So for those of you that don't know me, I'm Adyasha Mohanty. I'm a fourth-year PhD student in the NAV lab in the Aeroastro department at Stanford, and I'm advised by Dr. Grace Gao. So today I'm excited to present to you my dissertation topic, which is improving GNSS and camera vision fusion for urban localization. Localization is critical in the urban environment because it enables several applications, such as autonomous driving, augmented reality, Internet of Things. Even a pedestrian who is trying to find their way in the city uses GNSS and other sensors on a day-to-day basis. Because localization affects so many aspects of our life, we need to design precise and reliable positioning algorithms so that we can have enhanced user experience and enhanced safety. Yeah, there are many sensor choices that provide localization in the urban environment. Among them, GNSS and camera are popular and complementary sensors. GNSS stands for Global Navigation Satellite System, and it provides absolute positioning by utilizing a range of measurements from various satellites. So as an example, you have range measurements from these 4 satellites, and this is the absolute location. Cameras, on the other hand, provide complementary information because they capture the world around us. For example, cameras can tell you if what you're seeing is a pedestrian or a traffic light or a car. Let me explain a bit how GNSS works. So as mentioned before, there are satellites, constellations of satellites that orbit around the Earth in medium Earth orbit, and they continuously transmit signals towards a receiver that is located on the Earth's surface. There are various types of GNSS constellations, but the most common ones are GPS, which is the US one, Galileo, which is the European one, GLONASS, which is the Russian one, and Beidou, which is the Chinese one. Now, each constellation provides signals at multiple frequencies. For example, L1, L2, and L5 for GPS, and similarly L1 and L2 for GLONASS. Now, the receiver that is located on the Earth's surface measures its ranges to these satellites based on signal time delay. Then, utilizing a process known as signal triangulation, the user can precisely determine its own position and time. Even though we have been using GNSS since a long time, there are various sources of uncertainty that affect the quality of measurements, especially in the urban environment. The best case scenario that we have here is a direct signal from the satellite. But you may have a case where the satellite signal gets reflected due to the presence of buildings or even trees nearby. You might also have a case where the signal gets diffracted and you receive what is known as a non-line of sight or NLOS signal. And the absolute worst case happens when you have no access to the satellite visibility and the signal gets completely blocked, again, due to the presence of a structure. But note that as long as you have direct signals available, especially from high elevation satellites, you can always position yourself using GNSS. Now that we have looked at GNSS uncertainty, there are similar sources of uncertainty that affect the quality of camera measurements. The first source happens due to the presence of repetitive features. As an example, I've put a picture here of the Stanford main quad. And as you can see, all the pillars here look extremely identical, thereby creating ambiguity and difficulties in knowing where you are. Similarly, you might have errors due to the presence of glare and lighting variations, which can throw off any of the computer vision algorithms that are designed. The third source of uncertainty stems from occlusions when you have partial visibility due to the presence of either a structure or even a pedestrian that is blocking your field of view. And the last source of uncertainty can be attributed to change in weather, such as seasonal variations. As an example, you can see how different the city of Seattle looks in the summer versus in the rain. Therefore, it is important to account for all these sources of uncertainty in vision while designing and deploying our localization algorithms. So as mentioned before, we have looked at various sources of uncertainty that affect GNSS and camera. These can be broadly referred to as sensing uncertainty. The presence of sensing uncertainty leads to positioning uncertainty. Because we have individual uncertainties in GNSS and vision, during the sensor fusion process, you might have a situation where the uncertainty gets magnified or propagated, thereby reducing the quality of the final position and increasing our uncertainty in it. The objective of our thesis is to reduce this final positioning uncertainty. Now, one way to do this is to identify measurements that are erroneous or faulty and reduce the impact that they have on the final position. This category of methods is broadly referred to as fault identification and mitigation. But this has been successfully addressed in aviation because we have a very good understanding of what is considered safe. But directly applying these methods to urban environments is challenging. This is because urban environments are dynamic in nature. I mentioned the weather example before, but there are also buildings, trees, pedestrians, and other sources of errors from heterogeneous sources such as GNSS, camera, and even different kinds of vehicles that might throw off any localization estimate or notion of safety that we have. So the objective of my thesis is we want to detect and mitigate faults that arise during the sensor fusion process, but we also want to enhance the accuracy of each of these sensors, in this context, GNSS and camera, by using novel technologies such as neural networks. So to summarize my contributions, I'll talk about first, providing a particle filtering framework for GNSS and camera vision fusion and fault mitigation. Next, I'll talk about improving the accuracy of GNSS sensor by using Graph Convolutional Network or GCN. And lastly, I'll talk about designing an efficient and compact CNN or convolutional neural network for enhancing the accuracy of vision and then performing joint fault mitigation and state estimation. Now, during my PhD, I had the opportunity to work on various projects and work on these publications that helped me address the objective. But due to the interest of time, I'm only going to talk about 3 contributions today. So I want you to keep this slide in mind because this is going to serve as the outline for the rest of my talk. So to start off my talk, I would like to first talk about my particle filtering framework that achieves sensor fusion using GNSS and camera measurements, as well as mitigates multiple measurement faults. So first, let's take a look at the existing literature that has tried to tackle this objective. This can be broadly divided into 3 categories. The first category of works use Kalman filter. Some of you who use state estimation on a day-to-day basis might be familiar with Kalman filter and its variants, such as extended Kalman filter, uncentered Kalman filter. Now, the key challenge, though, is when we use Kalman filter for state estimation in urban environment, oftentimes we are making simplifying assumptions on the measurement model. These assumptions can create over-conservative estimates of the uncertainty and might even reduce the confidence that we have in our final position. The second category of works are referred to as receiver autonomous integrity monitoring, or RAIM. And I'll explain RAIM in a little bit, but the idea of RAIM was introduced in the 1980s to address fault mitigation for aviation. There have been several variants of RAIM that have been developed in order to perform fault mitigation for urban environment, but the literature there is relatively sparse. And lastly, there are other approaches that take inspiration from domains such as controls. For example, people have used stochastic reachability, a commonly used tool in controls, to bound the errors in state estimation and create models for these measurements. But the challenge, though, is that there are very few works that account for vision uncertainty along with GNSS uncertainty. Additionally, a lot of these methods treat state estimation and fault mitigation in a sequential manner. Now, this is challenging and problematic because in urban environments, if you accidentally identify the wrong fault and keep doing this for a sequence of time steps, then your state estimate might become very biased, and that might compromise our safety standards. So first, let's take a look at how RAIM works. As mentioned before, RAIM was designed primarily for the aviation community to address localization safety. Now, if you remember from my previous slides, we need at least 4 satellites in order to position yourself. But what if you have 5 or even 6? Well, in that case, RAIM can utilize the redundant measurements and assess their consistency with respect to the position that is estimated from using subsets of 4 satellites. And by using residual analysis or other statistical analysis techniques, we can both identify and exclude the faulty measurement. So as an example, let's say you have measurements from these 5 satellites. You compute the position using the first 4, you check the residual with respect to the 5th satellite, and then you deem that to be faulty. Obviously, this requires us to have 5 satellites in view. But as you can see, RAIM operates in an iterative manner. Can we do something better? Because in urban environments, there are sparse measurements due to the various measurement error sources that I introduced before. So we need a framework that lets us perform state estimation and fault mitigation while being able to work in the presence of few or no measurements. So to address this, a colleague of mine from the NAV lab designed Particle Rain, which is an improved GNSS fault mitigation method specifically designed for urban environments. Now, instead of assuming that only one candidate represents your position, you can instead create a distribution and assign weights to different position candidates. That is the idea of particle filter. Particle filters let us track multimodal uncertainty. As you can see, here is an example where various candidates can be likely positions, so we do not want to exclude any of them until we have some idea from the measurements. We can compute the weights that are assigned to these particles by using a similar mechanism as RAIN, but instead we can perform optimization by using latent schemes such as expectation and maximization. And instead of using a simple Gaussian to bound the uncertainty in the measurements, because we might have multimodal uncertainty, we can instead construct what is known as a mixture of Gaussians model, where each Gaussian has a certain weight assigned to it based on the confidence that this particular measurement is going to provide the correct position. So as you can see in the figure below, the weights of the particles directly reflect the confidence that we have in the GNSS measurements. And this framework is nice because it lets us identify faults even in the presence of less than 5 satellites. But the caveat though is that because this framework was designed for GNSS only, there is an upper bound to how accurate of a positioning can be obtained. So our contribution was to extend this to GNSS and camera sensor fusion from GNSS only. But it is not so easy, and there are 3 challenges that need to be addressed. The first challenge is we want to address the multimodal uncertainty that stems from camera images, as discussed before. The second challenge is because GNSS and camera are heterogeneous sensors, it is challenging to directly integrate a coarse distribution with a finer distribution and maintain a multimodal positioning estimate. And the last challenge is we also want to mitigate faults in camera measurements and ensure that we do not introduce any new faults during the fusion process so as to maximize the complementary characteristics of both sensors. So our solution to address these challenges is as follows. For the first challenge, we design a mixture of experts probability distribution that captures the multimodal uncertainty from camera images by using successive images between 2 consecutive GNSS timestamps. To address the second and third challenge, we propose and design a probabilistic fusion metric inspired by the idea of KL divergence, which is commonly used in information theory. And let me explain each of these contributions in detail. So we want a distribution to track the uncertainty in our camera measurements. But for that, we need to have a representation that is very generic and doesn't make any assumptions on the distribution, for example, the distribution being Gaussian. So for that, we leverage a mixture of experts or MOE model, which is an arbitrary collection of distributions where each distribution has a unique weight. Now, because we want to capture the uncertainty from successive images, how do we even do that? For that, we propose an improved map matching mechanism that uses scalable vocabulary trees. This can be divided into 3 main steps. In the first step, we create an image database by using collection of geotagged images, either from Google Street View or satellite images. Now, once we have access to these images, we can identify the key features and descriptors from these images and store them in a computationally efficient manner, specifically by using quantized k-means clustering. From that, we can obtain a tree where every node of the tree has these features clustered in a nice manner. At runtime, once our car receives a test image, we can perform map matching or image registration by scanning this vocabulary tree and then assigning scores to those images, which happen to be very similar to the ones in the database. After we have the similarity scores, we can pass them through a softmax distribution to get a probability distribution. So given an image, we can now construct a single mode, but we still don't know how to assign the weights to different modes, which indirectly represent the confidence in the measurements. For that, we propose the KL divergence metric. KL divergence is used in information theory to quantify the difference in information given 2 distributions. But for our case, we can modify and extend this because we know that because the GNSS distribution has already been made fault robust, by assessing the consistency of the resulting camera distribution with respect to GNSS, we can indeed achieve improved fault mitigation compared to the case when we had no GNSS measurements. So analytically, we can actually compute the weights that should be assigned to each of these camera measurements so that the resulting mixture of experts or MOE model minimizes the divergence with respect to the GNSS distribution. So let me explain how this works. We have unimodal distribution that we created from each image. We propagate them using IMU, which gives us access to the motion model of the vehicle. And this is just to ensure that we are synchronizing with GNSS measurements and also not removing a lot of measurements. After this, we take the GNSS distribution after applying particle rain, and we take the mixture of experts model whose weights have been already constructed by assessing consistency with GNSS. And then by assuming conditional independence, we create two things. We create the final state probability distribution, which is multimodal, but we also create an overbound on the positioning uncertainty. Now, due to interest of time, I'll only show the positioning results. We test our approach on real-world data sets that was collected in Frankfurt. So it's a 2.3 kilometer long data set and has naturally occurring GNSS faults, such as non-line of sight errors. We also create emulated data sets to stress test our approach. We add Gaussian biases and faults randomly. We also add vision faults, such as occlusions and blurring to randomly selected images. As baseline, we compare our approach against particle rain, which has been designed using GNSS measurements only. As metrics, we evaluate our approach against accuracy as well as sensitivity. And here's a list of all the evaluation cases. Now, let me explain the results a bit. If you look at the first table, we studied the RMSE, which is the root mean square error in 3D position, with respect to varying levels of non-line of sight errors in GNSS measurements. As you can see, for all the evaluation cases, our approach can indeed perform much better given the particle rain baseline. If you look at the right plots, you can see that for various levels of added bias, as well as added faults in GNSS and randomly added vision faults, our approach can indeed outperform the existing baseline. So this shows that our framework is successfully able to do two things. It can successfully mitigate the faults in camera measurements. It can also successfully achieve sensor fusion by mitigating the faults that might occur during the fusion process of GNSS and camera. Next, I would like to move on to my second contribution, which is using a graph convolutional network, or GCN, to improve accuracy of GNSS. Let me explain some of the existing works in this domain. So learning to the GNSS community has been becoming really important. And there are various categories of works that have tried to predict a position correction, which is the offset between your true position and the position given by your localization algorithm. Among these works, the first category of works leverage snapshot methods. What I mean by that is that they take the measurements at a particular time step and apply the positioning correction to those measurements. But because of this, they do not account for temporal relationships. Now, in literature, it has been shown that GNSS measurements have both spatial, which means that the errors depend on the position, but also temporal relationships. What that means is that the errors are also a function of time. The second category of works try to address exactly this. So they have designed temporal techniques by using recurrent neural networks or even LSTMs to provide a positioning correction. But a lot of these works do not use the strong prior that we have from model-based methods. For example, our understanding of satellite geometry and the different kinds of faults that we expect to see in the urban environment. And the last category of works combine both model-based as well as learning-based methods. This is really interesting because these methods let us leverage the power of our prior models, which is our understanding of how GNSS works, with something that can learn nonlinear relationships just by looking at data. The challenge, though, is that there's very sparse literature in this domain. In fact, there's only 2 works that have tried to adopt a hybrid method. And not just that, one of them has shown promising performance on real-world data. So we need to have more hybrid methods that can show promising performance on real-world data sets and not just simulated data sets. Before I can introduce my approach, let me summarize the benefits and disadvantages of both kinds of methods. So for model-based methods, which are typically weighted least squares or Newton-Raphson that have been used traditionally for positioning with GNSS measurements, they have indeed achieved high accuracy in open sky conditions. Open sky refers to the environments where we don't have any buildings or clutter that might block or diffract GNSS signals. And these frameworks also let us provide explicit modeling of the error sources by using domain knowledge. The disadvantage, though, is that we need to have expert knowledge in order to tune and overfit these parameters so that we can achieve the desired accuracy in different kinds of environments. And because of that, the accuracy can also get degraded in extremely challenging conditions, mostly because our assumption on the noise models differs significantly from the true noise. In the other extreme, we have neural network-based methods. They are really good at handling uncertain noise models and discovering nonlinear relationships by just looking at input and output pairs. The disadvantage, though, is that they may need or require large amounts of labeled and training data. Not just that, they may not even generalize to previously unseen conditions. For example, if your training and test distributions differ significantly. So our idea is that we can combine the benefits from both of these approaches in order to predict and provide improved positioning, especially for low-cost receivers such as smartphones. So we propose a hybrid framework that has two key aspects. We design a graph convolutional network, or GCN, that can represent diverse graph structures in the urban environment. We also provided better initialization and feature conditioning by using a Kalman filter. As you can see, there's a nice interplay between the Kalman filter and the graph CNN, where the Kalman filter captures temporal relationships in the measurements and provides initialization and input conditioning to the learning approach, which is the GCN. The GCN then predicts a positioning correction, which is applied to the initial position that our Kalman filter estimated. Here's a sample graph illustrating how do we even create this GCN. As you can see, the different nodes in the graph represent satellite positions, and clusters represent different constellations such as GPS, Galileo, and GLONASS. Now I'll explain in a little bit how we create the edges between these different nodes. But before that, let us first understand our design choice. We had many choices, for example, fully connected network or even recurrent neural network. But why did we choose a GCN? Well, that is because the graph structure naturally provides the ability to represent and learn the complex relationship of GNSS measurements with respect to errors such as multipath. Not just that, in the spatial representation of the graph, we can naturally utilize multiple frequencies as well as multiple constellations. Here's a figure illustrating how GCN works. So as you can see, we have different nodes in the graph. And then at runtime, the nodes aggregate information from all of its neighboring nodes and then pass them through a nonlinear operation, typically a neural network, and then gets its own updated node embedding. And this process happens concurrently for all nodes in the graph. So compared to a fully connected network, a graph CNN is much more efficient because all the nodes in the graph share the same weights and biases. Now in GCN, we are essentially applying convolutions similar to a CNN, but instead of fixing a set data structure, we can apply it on irregular structures such as graphs. The GCN takes two inputs. The first input is a feature matrix, which describes the graph signal on every node. And the second input is an adjacency matrix, which describes how should these different nodes be connected. An important property is that graph structures are dictated by graph isomorphism. This basically checks and tells you if two graphs are similar in terms of their node adjacencies. The classical way to check this is known as the WL test. This WL test is important because it represents the upper bound of how representative your graph CNN can get. And we will come back to this point in a few slides. Moving on to the design of our GCN. If you remember, this is the same graph that we had 2 slides previously. But now each of these nodes have a feature vector. The feature vector is a concatenation of 2 things. The first thing is a line of sight vector, which describes the satellite geometry with respect to the user. So it's a unit vector, and the first 3 elements of the feature vector represent the line of sight vector. The last element in the feature vector is the range residual, which is the difference between the expected and the received range measurements after being compensated for errors such as clock biases, ionospheric, and tropospheric errors. Now, the design of the adjacency matrix is a bit interesting. The intuitive way to design this would be to cluster all the nodes that belong to the same constellation because they have similar errors, such as satellite clock biases. But we can do something better. We can also connect nodes in the graph that are located many hops or many neighbors away. And this is important because, for example, if they have similar measurement residuals, that means that those measurements might share similar kind of errors, even though they are located in different constellations. And in this example, we established the connection by using an empirically determined threshold. For our case, the threshold was 5 meters. So we connected these two nodes because the difference was less than that. Moving on to the design choice of the convolution itself. So as mentioned before, the WL test upper bounds the representative power of the GCN. At the time that this work was published, GIN convolution was as powerful as satisfying the first degree WL test using simple architectures. Because of this, it offers us the maximum discriminative power among all GCNs. And because of this ability, it can also capture diverse set of errors in the urban environment. Let me explain how GIN convolution works. So we have the same graph. Now, let's say we want to update the embeddings of the center blue node. What happens is we perform an aggregation by taking that embedding and sum it with all the embeddings of its neighbors. We again pass it through a perceptron or another neural network and then get the updated node embedding. Now we have successfully generated updated node embeddings, but we still need to do something else in order to predict a 3D vector from the entire graph that can be applied to the position. So in other words, we need to reduce the spatial resolution of the graph in a successive manner without compromising the accuracy. For that, we apply mean pooling, which averages all of these node predictions, but we also apply additional fully connected layers, which increase the graph expressivity. This is important because in graph CNNs, you cannot just append layers of GCN, you cannot just append GCN layers because after a point, graphs encounter what is known as the oversmoothing problem. What this means is that all the nodes are going to have exactly identical embeddings, and thus we cannot capture any complex or any other errors. And after we have done all of this, our graph can successfully generate a position correction. We also evaluate our approach on real-world data sets. Specifically, we test this on the Google Smartphone Decimeter Challenge dataset, which is an open challenge on Kaggle that has been running for the past 2 years. As baselines, we compare our approach against both model-based methods, which are the weighted least squares and Kalman filter, as well as a learning-based method, which is the fully connected neural network. We make sure that all these baselines have been tuned so as to provide maximum performance on these data sets. As you can see here, with respect to every single metric, our approach can indeed outperform both model-based methods as well as learning-based methods, even on previously unseen and test data sets. So this is really promising because so far, none of the hybrid or even learning-based methods were able to achieve competitive or improved performance compared to existing model-based methods. But we strongly believe that by combining the advantages, such as the representative power of the graph CNN, as well as the strong initialization from the Kalman filter, we can indeed achieve competitive and even improved performance in challenging urban conditions. Moving on to the last contribution, I would next like to talk about using CNNs to improve accuracy of vision for GNSS and vision fusion. Before that, let me explain how CNNs work. So as you can see here, a convolution filter slides over an image. And by using combinations of such filters, we can apply them for any downstream task, such as image classification, object detection, or even semantic segmentation. At the time, people were interested in exploring CNN for different tasks. Among them, one of the such tasks was pose regression. What I mean by that is if you have access to training images of a particular geographical region and a trained neural network, then you basically have access to a compact map representation. Now, if you remember my first contribution, we had to manually create the database by using street view or satellite view images. And even at inference time, we had to scan the entire database so as to get the similarity metrics. But instead, by using a trained CNN, our inference task becomes much easier and faster. Not just that, CNNs for pose regression have been shown to have more resilience to errors such as lighting as well as motion blur. So to give you a spectrum of the different kinds of architectures that exist, we first have PoseNet, which was the pivotal architecture to perform pose regression using a combination of images. Even though it achieved promising performance on a variety of tasks, it was very bulky and expensive to train and even had a higher memory footprint. In the other extreme, we have architectures such as MobileNet, which are these really small and compact CNNs that can even be deployed on your smartphone. But they have been only explored for tasks such as image classification, so for knowing if something is a cat or a dog. But that's not really useful for our case because we want to get the absolute location from a given image and then later use it for our task of sensor fusion. So in order to satisfy our objective, we need to design a lightweight and efficient CNN that can perform post-regression given a single image. So our proposed CNN looks like the following. We used a combination of squeeze and expand modules, which was proposed in SqueezeNet, a prior work. It is essentially a mix of 1x1 and 3x3 convolution filters, but because of this compact architecture, our model size is only 5 MB compared to 50 or even 100 MB of existing works. We also make sure that our small architecture does not provide or does not lead to overfitting on a variety of urban data sets. For that, we apply dropout right before the last fully connected layer. And we also train this on diverse urban scenes to capture a variety of weather as well as lighting variations. Now that we have trained the CNN, we can actually regress a candidate pose or the expected position of our car, for example, given an image between successive GNSS timestamps. Now that we have formed this candidate pose from a CNN, we can bring back the same concepts that I spoke in my first contribution, which is this idea of having a particle filter to represent multimodal positioning uncertainty. But we can even make it better by combining it with fault robust optimization. So what happens at every time step is we generate candidate poses given a sequence of images. We also have access to range measurements from multiple satellites and particles, which represent our position hypothesis. By utilizing both of these things, we can create range residuals, both from GNSS as well as camera. Now, traditionally, a mean square error loss would not be able to outweigh or deweigh the influence of significant outliers on the loss function. Hence, instead, we use a modified loss known as M-estimator, and there are various choices of loss function, but the key idea is that they help us mitigate the impact of extreme outliers on the final loss function. Now, after applying this robust loss, we can analytically compute the particle weights so that we are minimizing the residuals from GNSS and camera in a joint manner. So after this, we can directly compute the particle weights. And as you can see here, behind this framework, the M-estimator is essentially making sure that any measurements that are faulty should be assigned low weights, and any measurements that are correct should be assigned high weights. We also test this on the same urban driving data set that was collected in Frankfurt. But now we have two baselines. The first baseline is a dense CNN, which is a much larger architecture that has about 50 MB parameters. We also have a second baseline, which is a particle filter that achieves loose GNSS and camera vision fusion. This is the same architecture that I discussed in my first contribution. And we have a list of different metrics as well as evaluation cases. But due to interest of time, I'll only show a few here. As you can see, even with added vision faults and varying level of satellite faults and satellite bias values, our approach can provide competitive or improved performance compared to existing baselines. So by combining the benefits of robust optimization with particle filter, as well as by improving accuracy of the vision-based module using our compact CNN, we can indeed achieve improved fault mitigation and higher positioning accuracy in urban environment. So to summarize the first part of my talk, we designed a particle filtering framework that can detect and mitigate multiple measurement faults in GNSS and vision fusion. We use neural networks to improve the accuracy of both of these sensors independently. So for the GNSS module, we designed a Graph Convolutional Neural Network and provided it better initialization from the Kalman filter to achieve improved accuracy on smartphone measurements. For the vision module, we designed a compact and efficient CNN that can regress candidate poses and helps us achieve improved vision accuracy. But there's a lot of opportunity for future work, and I would like to highlight 3 of those here. The first opportunity is instead of training the Kalman filter and the Graph CNN separately, we can indeed unify them and establish an end-to-end architecture so that we can backpropagate the parameters of the Kalman filter that help us achieve improved accuracy. To achieve this objective, we submitted an abstract to the upcoming ION GNSS conference that was accepted. The second opportunity is instead of using manual features such as line of sight vector and measurement residuals, we can leverage schemes such as attention mechanism that can help us identify which of these features are crucial to achieve the desired accuracy. And lastly, there's a lot of scope for performing online adaptation by using learning based on the environment. As a simple example, if we are navigating in open sky, we know that we should have higher confidence in the GNSS measurements compared to, let's say, we were navigating in a tunnel or even in a dense urban environment. Now, moving on to the second part of my talk, I would just like to highlight a few works. I think Professor Gao even hinted at this during my introduction, but one of the projects that I worked with was done in conjunction with Toyota Research Institute, or TRI, as well as Dynamic Design Lab, or DDL, here at Stanford, led by Professor Chris Gerdes. The objective of this project was to design algorithms that can help us achieve precise relative localization for autonomous tandem drifting cars. Now, this is really important because understanding the limits of a localization algorithm at the stability or limits of vehicle stability, such as drifting, can help us derive key insights as to how should these cars behave in terms of the localization stack when we are undergoing aggressive maneuvers or even navigating on icy conditions, or even during aggressive entry and exits on the freeways. Towards satisfying this objective, I had the opportunity to work on two projects. The first project involved testing our localization stack using low-speed real-world data that was collected at Stanford campus. For that, we designed a standalone localization system that fuses ultra-wideband, or UWB, sensors along with GPS sensors and provided sub-meter level accuracy on trajectories that were collected by driving the cars on campus. The second project that I have been working on is introducing a heterogeneous system. So we have the two cars that are drifting on the ground, and we have a drone that is directly flying on them and provides a bird's eye view, so that in case of failures of the standalone localization system on the cars, the drone can still provide us a redundant estimate of the relative position between the cars, so as to satisfy our safety objective at all times. So I would like to acknowledge the following people. First, I would acknowledge the Stanford Graduate Fellowship, or SGF, for giving me the opportunity to work on a variety of projects during my time here. I would also like to acknowledge Ford for allowing me to work on sensor fusion algorithms and utilizing my background knowledge in aerospace to the urban environment.